Hello, and welcome to Module 4, where we will be having a deeper dive into probability. We'll start with an introduction, and we will learn about the fundamental probability concepts and apply these rules of probability to inform future likelihoods. Every day, we make choices about issues in the presence of uncertainty. By figuring out the chances of various events happening, we're better prepared and equipped to make a more desirable choice. This chapter presents the fundamentals of probability and the tools needed to frame and address many real-world issues involving uncertainty. So let's get started. Let's talk about what is probability and what is uncertainty and likelihood. So probability is the likelihood that something will happen under uncertainty. These concepts form the foundation of statistical inference. For example, how the Federal Reserve adjusts interest rates based on expected inflation and growth of the economy. It's uncertain what will happen. What they do needs to be based off of the expected likelihood of the future economy. The value of probability is between 0 and 1. Where 0 indicates no chance and 1 indicates a definite event happening. This is why people say sometimes there is a non-zero chance of interest rates increasing in the next 5 years. And that means there's a likelihood that it will happen. It's not non-zero. For those familiar with the sigmoid function, we can think of probability as a value between 0 and 1, where you see in this curve right here at the bottom left corner of my screen, where 0 means no chance and 1 is definite. And this likelihood of an event is that curve between these two intervals of 0 and 1. So usually we don't have 0 or 1 certainty, we have somewhere in the middle. And by using probability rules, we can better ascertain what is the likelihood of something like the interest rates rising in the next 5 years. Before we go into that, let's establish some structure around how we would calculate probability. First, we need to define an experiment, which is the process that leads to one of several outcomes. The world is uncertain, so we need to test the actual outcome of our expectations and collect data to inform the likelihood of the event occurring outside of the experiment. So we have our little laboratory setting, and we want to understand these patterns that would result in a likelihood that we would expect to see outside of the laboratory setting. While we do this, we need to define a sample space. This is all possible outcomes of the experiment, and this helps define the problem we are facing. Are we trying to predict likelihood of a binary variable, such as heads or tails, which has true or false, just binary, that's why it's 2 different options? Or are we faced with a categorical variable, such as the letter grade? What's the likelihood that you'll have an A given how many hours you've studied? We need to know all the possible outcomes before we can test them. And by all possible outcomes, for probability, it needs to be exhaustive. So for the grade letter example, we would need to know what are all the different options of grades before we can say the probability of an A over probability of a C. Another example would be considering dice and rolling them. We have a sample space, which is all the different outcomes that are possible, which is 1 to 6 dots on your die. And we want to ensure that we have exhaustively listed all possible outcomes. The last component is measuring when an event occurs within the sample space. This consists of one of the possible outcomes. Going back to our dice example, such as rolling a 2 when throwing 1 die, we want to know 1 out of 6 of that would be a 2. Since there's 6 options and we're only looking for 1 outcome in particular here. There is another concept to consider here, and I mentioned the term exhaustive, but now we're thinking of an exhaustive means you list all the possible outcomes. There's no other number on a die 1 through 6 that can happen. You can't see 8 or 9 on just 1 die. So we're exhaustive here, but thinking about now mutual exclusivity is a different concept of that, where only one event can happen without any overlap between outcomes. such as when throwing one die, the outcome is mutually exclusive. You can't have both a 2 and a 4 show up on the die at the same time. It can't be both, is really what mutually exclusive means, that they are separate from each other and there's really no fuzziness in between. However, in real life, there's usually a lot of fuzziness and we don't have these nice clean boundaries where we would really see more overlap between categories. One example from professional experience is when I was defining a taxonomy of environmental social governance events for tagging different sentences that relate to sentiment around how a company is performing in their earnings transcripts as it relates to sustainability. A sentence could be classified as both governance and as a social consideration when something such as their diversity in the board and executive team that might relate to both a social consideration and a governance consideration. So that's an example where this concept of diversity is not mutually exclusive to one category of social or governance compared to something like an environmental policy has a nice clean gap, and we can think of these things as mutually exclusive. It doesn't fit into more than one. But that was just an example of how most things in life aren't so clean where we could say they are mutually exclusive from each other. But when we have something like a dice in this laboratory experiment, those would be mutually exclusive. When we create an experiment, we must define the potential outcomes or combinations of outcomes to form new events. First, we can consider the union in the top left corner, which shows the intersection of both category A and category B. Thinking back to that taxonomy example, we would consider A to be a governance event and B to be a social related event. And looking at the union between, we would have an assessment of a company's investment and policy on social and governance considerations. And we use Venn diagrams to represent this space. And Venn diagrams were named after John Venn, who invented the diagram, and it uses his last name. On the right, we have the intersection of two events where there is possible outcomes that exist in both A and B. This would be valid for that example about a company discussing a new diversity policy in their executive team, that we would classify this as both governance and social by the definition of our taxonomy. These fit into both bins. And this would just be the center part where there is not mutual exclusivity between the different factors. There's overlap between. Lastly, we must define anything that exists outside of our factors that we defined. This is the complement of all possible outcomes in the sample space that are not A. And again, this is just to account for all the different bases that happen. So for the grades example, you would have A through F, and we don't have anything that's not A through F. But for something like the ESG example, there could actually be no ESG consideration, and that would be just not within these E, S, or G buckets. So we need to also think, okay, what if it's not any of these things as well? The requirements of assigning probability is that the probability of any event is between 0 to 1, and the sum of all probabilities that are mutually exclusive and exhaustive equals 1. So similar with that dice example, the probability of any of those faces coming out when you roll it will all add up to 1. If you take the probability of 1, probability of 2, probability of 3, so on till 6, it's 1 out of 6 times those 6 faces. So that would all equal 1 if you added them together. And this allows us then to calculate the proportion of an occurrence happening. So as an example, let's consider the probability of an Olympic athlete earning a gold medal. Let's say there is a 10% chance that they win the gold medal, a 15% chance they win silver, and so on here as we see in this probability table. We can assign a probability given our expectations of this athlete's past performance. And these outcomes are mutually exclusive and exhaustive because there's no other options outside of these. And thinking of gold, silver, bronze, those are the options. And then similar to the prior page where I showed the samples outside of this scope of no metal one. So it can only be one of these 4 options. And we have the probability as a proportion to the right in this chart. So notice the probability when summed up will equal 1. And if we wanted to calculate the probability of winning a medal, we would take the sum of probabilities for gold, silver, and bronze, which added up equal 45 or 0.45, 45%. And we could also just subtract 0.55 from 1 and arrive at the same outcome. So we really want to think about this space as being almost like thinking of like the pie chart of if you were thinking either metal or not metal, that 55% would be no metal. And then the breakdown between gold, silver, and bronze would make up that other proportion. And we divide by the denominator depending on what it is that we're trying to solve. So something like probability of silver, we would divide 0.15 by the total of events. But if we said, let's say out of this athlete winning a medal, what's the likelihood that it's silver? We would need to change our denominator to be aligned with what it is we're trying to solve for. So given that they win a medal, we wouldn't want to include the 0.55 of them not winning a medal. And a lot of the homework questions will be similar to this type of framework of thinking. Similar to our discussion about randomness, when we're thinking about how things are distributed and how they relate to each other, we should talk about the law of large numbers, which comes into account when we are measuring the sample space. Because we're trying to think of how this sample space would be representative of the wider population. Thinking of, we're just throwing a die 5 times and we want to know the likelihood of seeing a 2 out of 5 times. That's just 5 times, but how would this relate to if we threw it 500 times? Would we see the same probability arrive? And this is related to this law of large numbers. When we run an experiment a large number of times, we are more likely to witness the true probability. When we think about flipping a coin 10 times, you might not see the distribution, a fair coin, of course. You think you have a 50-50 chance of seeing heads, tails, but if you flip that coin 10 times, you might actually see more heads than tails. And that's just randomness. It's this likelihood that it's not 50-50 unless you actually flip it enough times to be able to see this true probability that you have an equal chance of heads or tails. So if you were to flip it 100 times, you would get closer to the true probability compared to only flipping it 10 times, where you might experience a fluke where you get really lucky and get tails all 7 times. But we can use probability to actually define these different likelihoods. I wanted to show this interactive demo that shows this distribution of balls from a Plinko board that you might see at a carnival. And we're going to run an experiment where we start to see the true distribution of where the ball might land. So I have it already loaded, and I linked to it on our Blackboard, so you can also play around with it as well. So you have a Plinko board, and let's say you win a ticket if you guess which bin, 0 out of 12, or if we wanted to make it few amount of rows, we could. So you win a ticket if you guess where the ball might lead. So let's say we guess the probability of a ball leading into bin 6, because it's in the center. Maybe we'll say there's a 2 out of 12 chance, but let's just see what one ball might do. And if it goes into, so we were off by 1, it went into 7. So now we might continue down this path to see what's the likelihood that it gets into the one we think. And because of this randomness where it could go left or right at any chance, it might not actually go into the one that we would assume, which is right below it. It goes a little bit to the left and to the right. So as we keep seeing these individuals, now we're seeing 9 is the most likely number that can happen. And it calculates a couple of summary statistics right here, which is what's the average, what's the standard deviation. And now let's see what happens if we run this for many balls to fall down. This would be an example of this law of large numbers, where what would we expect to see in this distribution might now be witnessed once we have a larger sample size. So I'm going to hit run, and now we have all the different balls coming down the chute. And because of this simulation, we can now see at a more rapid pace that we're starting to see this true probability distribution of where the ball might lead. And now it's starting to look like something that we would expect to see, which is this nice Gaussian distribution along the center. All right. So feel free to play around with this more. They have a different intro and lab along with it, but the core concept is when you start to have a larger sample size, you see this law of large numbers, where now the true probability of having a ball fall and hit into 6, you start to witness that distribution in a more truer sense. And we've only really been talking about one event happening over another, but what if we wanted to combine the probabilities of events? First, we can state that the sum of all assigned probabilities must equal 1. We can think of the complement rule as subtracting the probability of an event minus 1, because the sum will equal to 1. And pretty much we can think of this as what is the probability that event will not happen by subtracting that probability from 1. Next, we have the addition rule, which states how we can calculate the probability of either A or B of occurring. And A or B, these just represents the, thinking of gold or silver for that metal example. We need to consider that sliver in the intersection of both events occurring if these events aren't mutually exclusive. And we would overcount the probability if we simply added both probabilities. So we actually subtract the union or joint probability from the events of A and B happening. The values of total likelihood for an event is represented by the unconditional probability or the marginal probability, since this value is calculated in the margins of the contingency table, which we talked briefly in the last chapter, but we'll get into more here, which shows the breakdown of different counts when you group it in different ways is a contingency table. So, and that shows the sum of everything in that row or column. And we're talking about marginal probabilities, and those sums are calculated in the margins. So that's what you should think of when we're talking about marginal probabilities, is usually what's the likelihood we have X given we see this many counts of Y. Another term we should define is conditional probability, where this is the likelihood of A given the condition of B. For example, what's the probability of finding a job given your prior work experience, or how many years of prior work experience? And this is calculated by taking the joint probability of both A and B and dividing it by the dependent variable, or the probability of B in this case. So we can rearrange the conditional probability formula by taking the probability of A given B and multiplying it by the probability of B. And this content is aligned in the textbook for further descriptions and different context, if that'd be helpful outside of this presentation slide deck. We will have to look at the marginal and joint probabilities in this example. If we were to consider a family with 2 unknown children, if we're trying to, I think this is actually from like a riddle that someone submitted very long ago into some newspaper about if you could, what's the probability of having 2 children that are both girls? We can use the marginal and joint probabilities to solve this. Then we can make a joint probability table and sum these probabilities to figure out the differences. So usually when we're trying to tackle any of these problems, it's helpful to list the different options. And I really encourage you to use a pencil and paper to just draw out the different likelihoods as a table. And we'll get into these different calculations in this chapter later in the slides. But we want to first acknowledge that the events are independent from each other. And that means the likelihood of having a second child being one gender doesn't have any relationship to the first child's gender. These things are independent from each other. So similar to rolling a dice, it's independent of what you originally rolled, the next roll you have. Each observation is independent from the last one, compared to something that's dependent of picking marbles from a bag and not replacing, where the likelihoods would change depending on what you previously picked from the bag. So other assumptions, it's always good to define any assumptions, because again, we're thinking all the different things that could happen. So our assumptions is there's an equal likelihood of a child being either a boy or girl. The gender of the second child is independent of the gender of the first child. And we have possible outcomes where one is conditional on the events that the older child is a girl is 1/2, and the other outcome is conditional on the event at least one child is a girl. So thinking about how we're thinking just on the second one being a girl compared to the second one where it's both being girl. So we'll talk a little bit more about that as we go through an example. But before we dive into that, I just wanted to define a little bit more about these independent versus dependent events, which I was talking about with those marbles and with the dice rolling. So similar to our discussion of independent and dependent variables when we were talking about graphing, income related to how much you spend, we can think of independent events of two isolated events that have no interaction between them. So again, thinking the second child's gender is completely independent of the first child's gender. Okay, so back to our example, we're going to start to calculate these different things. And again, as I mentioned, having a piece of paper just to write out all the different likelihoods that could happen. So you have two children. The first one could be a boy. The second one could be a girl. That's one option listed here as one. One could be a boy. The second one's a boy. That's option 2. And girl, boy as the third one, because now we're thinking order matters, because our initial question is the probability that both children are girls. So 1 and 3 are actually different probabilities, rather than it doesn't matter the order, where BG might be something similar to GB. The order here matters. And then the fourth option is that both are girls. And now let's put this on a table, as you see here in the bottom right-hand corner. So the first child, we think of this almost as, if you're familiar with like biology, of thinking like a Gantt chart of you have the different options at the top, and on the vertical, you have how they relate to each other. So you have the first child and the second child on this graph, or a table rather than a graph. So we put these marginal probabilities, since there is a 50-50 chance of having either a girl or a boy for the first child, and a 50-50 chance of having a boy or a girl for the second child. And similar to the binary outcome of a coin flip, we can either have boy, girl, boy, boy, and girl. So we have these 4 possible outcomes, and the probability of getting any one out of these 4 outcomes is a 1 in 4 chance. Now we want to say the probability the first child is a boy and the second child is a girl. This is the joint probability. So we multiply the probability of the first child being a boy and the second child being a girl. Both are 50-50 chance, and we take the product, which is 1/4. Then we can get into the conditional probability that given the first child is a girl, what is the likelihood of the second child being a girl? And we use the joint probability and divide by the marginal probability, where the joint probability is 1/4 and the conditional probability is 1/2. So the probability that the second child is a girl, given the first child is a girl, is still 50-50. But now we consider the conditional probability that both children are girls, and we take the product of the 2 events, and the probability the first child is a girl, which is 1/2, and the probability the second child is a girl, and that is now 1/4. We can also look at the complement and calculate at the probability of having at least one child being a boy. We would add the quarters together between the three other options, and we could sum that to 3/4. So the probability of the first child being a boy or the second child being a boy is divided 1/4 by 3/4, which is 1/4 times 4/3, or 4/12, which we reduce to 1/3. Next, we'll get into contingency tables, which are really helpful for examining the relationships between different categorical variables. It shows the frequency between X and Y, where each cell represents the number of observations for the pair of X and Y. Here is an example from Determinants of Economic Growth, which is from the OECD, thinking about different GDP, population growth. Oh, actually, so this is just determinants of economic growth. There's a category of if the member of this country is in the OECD. So we have 121 countries and features such as GDP, population growth, if the country is an oil producer, if the country has better quality data, and if they're a member of the OECD. And OECD is the Organization for Economic Cooperation and Development. So this is just I thought an interesting data set we can play around with for our class. And we can try to calculate the probability of a country having better quality data, given that the country is a member of the OECD. And the way we would do this is by taking a contingency table to sum the difference between if the country is a member of the OECD compared to if they have better I think it's the quality data, which is given by this variable inter. So we would see these marginal probabilities in the margins that we can see probability of being in the OECD and having high quality data. We can now start to calculate these probabilities that are conditional on each other. So we would take 22, which is the union of A and B of those factors, or OECD and having better quality data, and divide that by the sum of having quality data, which is 75. So we can say the probability is 30%, which you would see below when we start to just calculate these proportions or 0.29333. We can also think of the contingency table as a joint probability table, where we can divide each cell by the total number of observations. And notice how the probability would all equal 1. We can interpret this as the probability of being an OECD country and having quality data is 43%. So it's interesting to see that the probability of being in an OECD country and not having quality data is 0. So any country that's in the OECD has higher quality data. And perhaps this is indicative of the different governance and institutional structures that might exist, where more transparency, more proactively providing quality data because they are a member of this economic cooperation and development group might have some relationship between these different categorical variables. So we just discussed how we can think about conditional and joint probabilities by using the sum of how often this occurrence happens and dividing it by the different features we're looking at. Next, we'll get into Bayesian theorem or Bayes theorem. But first, I wanted to talk about who is Bayes named after. I think it's kind of interesting, his background. We will talk about Reverend Thomas Bayes, who is a British minister, and he studied logic and theology, but he's the founder of an entire field of study known as Bayesian Statistics. And this is usually contrasted against a frequentist approach in statistics. You have Bayesian and frequentist approach are usually the diverging sides, and The most important difference rests on this notion of having your prior belief actually inform the likelihood of the probability outcome and how that might change based on the strength of your belief. So we'll talk now more about Bayes, but just thinking about if you're thinking, what's the likelihood that something might happen, you can actually use your prior understanding or subject matter expertise to say, I know that this is very likely to happen. So you would establish that as your prior, and then depending on what actually happens, you can start to adjust and say, oh, okay, maybe I was a bit bullish on this and it's actually something a little different than what I anticipated. You actually encode your prior understanding into the likelihood outcome, compared to frequentist, which really takes just the observed frequencies and divides it by each other. So most of what we've discussed is this frequentist approach. And now let's talk about a Bayesian approach. So talking a bit more about this English statistician, philosopher, and minister, the Bayes Theorem, which is defined next slide, is a solution to the problem of inverse probability. And Bayesian probability is a whole school of thought based off this approach of calculating the conditional probability distributions. It's at the core of most estimation approaches and probabilistic machine learning techniques, risk assessments, mapping, and information theory. And Bayes' theorem uses this total probability to break down the likelihood of an event and measures how it has been affected by a new piece of evidence. We use this in order to estimate the probability of an event when data is scarce. We use the total probability rule to express the likelihood of an event broken down into the joint and conditional probabilities that support that likelihood of happening. To calculate the probability of an event, we look at the sum of probabilities and the intersections between A and the likelihood of other mutually exclusive and exhaustive events occurring. We'll call them B for now. We can see A is comprised of an intersection between B and the complement of everything that is not B, or we can think of this as B raised to C as the complement of everything that's not A. And according to the total probability rule, this probability is the sum of the intersections. We derive this probability from the conditional probabilities. We also need to be able to adapt these probabilities for when new information is seen. We do this with the prior and posterior probabilities. The prior is everything you know ahead of time, and these can be assumptions or your prior knowledge and experience on the likelihood of a future event occurring. Then you would measure the frequency of how often that event would occur and update the probability. On the basis of new information, we update the prior and arrive at a conditional probability, and that's called the posterior probability. This is Bayes' theorem. And the core, again, is using this prior probability. That's the main difference compared to a frequentist approach, where using this prior, we collect data and measure the outcome of events occurring and update that prior probability to compute the posterior probability. And here is the formula from Bayes' theorem. Oftentimes, the joint probabilities needed to compute the total probability are not explicitly specified, because we might think of all the different features that might need to be computed in these joint probabilities. So we might not have them explicitly stated. Therefore, we would multiply the probabilities from the conditional probability that the event happened and that the event did not happen. We simplify it in a sense. And the total probability rule is needed to derive Bayes' theorem, which is the procedure used to update probabilities based on new information. For an example, suppose we know that 99% of individuals who take a COVID-19 test are negative for COVID. Our prior would say 90.99 is the likelihood. So this is just our prior knowledge that most people who take a COVID-19 test are negative. But suppose an individual takes the test and the results indicate that the individual tested positive. we would update our prior probability to compute the posterior, which is the conditional probability based on the information that COVID-19 test detected positive. In this case, we might not have explicit information about the joint probability, but we can use the Bayes theorem to balance between our prior knowledge and the outcome that happened to calculate this posterior probability. So going into this example of what's the likelihood of testing positive, given this prior that 99% will test negative. So let D equal COVID was detected and T equals not detected. We can calculate the complement of not having COVID, which is 0.01. So that's just 1 minus 0.99. And that's this complement of not detecting COVID. Next, we formulate the probability of testing negative, given that you're actually positive, which is the probability of detecting COVID, given that you are actually negative for COVID. And let's say this is 0.95. We want to find, this is kind of thinking now again around what's the likelihood that you have it and there's no false positives in the test outcome where maybe they get it wrong. We think of this, the actual positive as 0.95. We're just thinking, we're putting the numbers in the chart of what the likelihood is. So now what if the probability of, I think I might have actually said this wrong. So we think about the testing negative, given that you're actually positive. So that would be a false positive. Testing negative, given that you're actually positive. So that would be a false negative. So you actually had COVID, but you tested negative since 0.99 of tests are negative. So that would be 0.95. And the probability of, these are just thinking of before you get your tests, there's a 95% chance that you might not have the test detect COVID, which is a high chance. So this is all dummy data. This is not real for how things actually work. It's just to demonstrate these different uncertainties that might exist. So what's the probability of detecting COVID, given that you are actually negative for COVID? So that would be a false positive. So the test says you do have COVID when you actually are negative. That would be 0.005. Okay, so now we have these different likelihoods conditional of having COVID given that you tested positive or negative. Now we want to find the probability that you do not have COVID given that this test was positive. And we can use Bayes' theory for this, where the first column represents the prior probabilities and the second shows the conditional probability. We first calculate the denominator with the total probability rule and the probability of not detecting COVID. We first take the union of predicting COVID, given that you do not detect COVID and you actually do have COVID. So we multiply these, which equals 0.00495, which is 0.99 multiplied by 0.005. Next, we calculate the opposite, where you do detect COVID, given that you do not actually have COVID, which is 0.95% time likelihood of falsely stating COVID is present, which is 0.01 chance of an equipment error. So joining probability is 0.01 times 0.95 or 0.0095. Then we would add these together for 0.01445, and this is the total probability rule. And that would be the total probability of detecting COVID-19. Now we can divide the joint probability of having COVID, given that you did not test positive, divided by the likelihood of testing positive. And this is 0.3426. So the prior of testing negative was 0.99. However, now we see the posterior of the individual testing negative is now revised downward to 0.3426. So this example shows how we have these prior understandings of false positives, of having a test tell you you're positive when you're not, or false negative, which would be worse, where the test tells you you're negative, but you're actually positive, predicated on our prior, which is saying 99% of people who out of 100 tests will test negative. And because we had an individual test positive and they were actually positive, now we would change our posterior and revising that to a more truer sense of 0.3426 rather than 0.99. We can extend this analysis to include an exhaustive number of events, and the total probability rule will calculate the probability for each event. And that is the way we would add all the different likelihoods together to have this total probability rule. Let's go through another example about an analyst predicting the likelihood of inflation rates going up the next year. There is a probability of 0.20 or 20% probability that inflation will go up significantly, a 50% chance inflation will go up only marginally. So thinking just whatever your sense of extreme inflation versus not so bad, and a 30% chance that inflation will just not increase at all. This analyst also considers that the probability of interest rates going up is 90%, with significant inflation, 40% chance it will go up if there is marginal inflation, and 0.10 if there is no increase in inflation. And I use this example because usually interest rates are somewhat related to future expectations of inflation, and these things are correct each other in a sense. So based on these estimates that this analyst conjured, what is the probability that interest rates will go up given the inflation that we exhibit in the next year? So we start with the priors and then state the conditional probabilities. We use the total probability rule and calculate the joint probability as the product of the conditional probabilities with their corresponding prior probabilities. The probability that interest rates go up, given inflation has increased significantly, is 0.90 times 0.20, which would equate to 0.18. We calculate this for each scenario, and then we take the sum of all conditional probabilities, which is equal to 0.41. This is the marginal probability that interest rates go up. We can then calculate the probability that inflation has increased significantly, given that interest rates have gone up. And this is the probability that interest rates have gone up significantly, increased over the marginal probability of interest rates going up. So 0.18 over 0.41, or this would equal 0.4390, which we see in our different columns as we do these different calculations. Our prior probability of significant inflation is now reviewed upward to a posterior probability of 0.390. And that is the last example we'll go through for this chapter. In this module, we reviewed the core concepts of probability by defining unions and joint probabilities, conditional probabilities. We talked about thinking different outcomes and how law of large numbers, once we start to take many samples, we'll start to see the true likelihood observed. And we talked about Bayes Theorem, which really uses these different concepts in an uncertain world, how we can use our prior understanding of how things might work, and we collect enough data, we see what the different outcomes are given the occurrence frequencies, and we use these different contingency tables to start to calculate the corresponding occurrences between different features. And we use these different theorems like Bayes' theorem to start to calculate the likelihood of different things happening given our expected outcome. And we start to revise to find the truer outcome of the probabilities. So with that, I will conclude this presentation and we will dive into the Python demo.